So, good morning, everyone. So, we'll continue this lecture series. Likewise, yesterday, 24, we will today again take 1 hour lecture and then a 15 minutes break, and then we'll continue.
Hear me? Do you hear me?
Yes.
So, uh, we are dealing with uh, uh, entropy, von Neumann entropy, Heron entropy, Kohlev's quantity, and maybe people who are coming from physics, they are not very much associated with these subjects. So let me again try to tell you what actually we are doing. It's very simple. And if you remember that the last that I was trying to tell that if mutual information between Alice and Bob is greater than mutual information between Alice and Eve, if somehow this can be assured, though this cannot be assured of the laws of classical physics because classical world everything can be copied or everything can be distinguished. So this cannot be guaranteed, but if somehow we can guarantee it, then we can generate secret key with the range where the range is difference between these two quantities. But to make life simple, let me tell you by some examples what actually we are going to do in quantum world. And quantum world is different from classical world in which sense there are states which cannot be distinguished, though they are different states. In classical world, every two distinguished different states can be distinguished. But in quantum world, even to pure state, if two different pure states may not be reliably distinguished. This is one thing, what cannot be copied. And another there is a measurement tool which collapses things to a particular subspace for which you have got some eigenvalues. But to make life simple, as I was trying to tell, what actually we are going to do. Consider a state of states. Let Alice has access to these four different states, and Alice wants to communicate some information to Bob via this by sending these states. Can you tell me how much information Alice can convey to Bob? This is a single particle. So how Alice will choose the set of states so that he can send the information reliably to Bob? That means either Alice will say 0, 1 for sending one bit of information, 0 going to 0, 1 going to get 1, or Alice will say, because this set can be distinguished. So though there are four states, using those four states, Alice will not try to send some information reliably to Bob, 2 bits of information. 2 bits of information in principle can be encoded because there are four states. But that will be risky because Bob will not be able to distinguish. So Alice has to make sure that at least Bob can distinguish among them. But if Alice has not a priori decided which set he is going to choose, Alice has to make some communication to Bob that I have choose this particular orthogonal. If that is not done, then Bob cannot reliably distinguish. So by some phone communication, Alice has to tell whether he is sending this set or that set. This will appear in our discussion. So Alice has to choose the set of states from a large class, set of states such that if Alice send them, of course, through a perfect channel, then Bob will be able to distinguish among them. Alice has to make sure. This is one thing. Another thing, because here I have taken two-dimensional Hilbert space. So with how many states you can pack them so that they can be reliably distinguished? It's two-dimensional, so only two orthogonal states. So by two orthogonal states, you are actually packing the whole Hilbert. So idea is you choose the states such that for the whole Hilbert space, you take orthogonal sets so that it packs them optimally. This is one thing. Another thing is privacy amplification. See how that Alice has to send more information. Alice has four mutually exclusive information or that's 0, 0, 0, 1. Now Alice can encode them in some four possible quantum states, and we also assume these four states are orthogonal. So if these states can be sent to Bob reliably or through a perfect channel, then of course Bob will be distinguished among them and can get these two bits of information. But the channel is such, but it's not some realistic channel. I am just thinking about it. So these can be sent to Bob, but at the same time, I am choosing four states. Now what happens when Alice sends A1 to Bob for if the information is 0, 0, then Alice will send A1. If information is 0, 1, Alice will take it this way. But what happens in the channel, it is artificial, of course, that if gets Chi1, in this case Chi2, in this case Chi3, in this case Chi4. Now let me ask you, this is qubit state. This is a state in some four-dimensional state. So that's why these four are distinguishable. But these I have taken, Chi1, Chi2, Chi3, they are qubit states. And this is a rho. So rho has two decomposition. Rho can be written as equal mixture of Chi1, Chi2, as well as rho can be written as equal mixture of Chi3, Chi4. Now the character of the channel is this. Now Alice wants to send some information to Bob, which Alice Bob will not, sorry, to Bob, which he intends that he will not get any information. So can you tell me a protocol by which it can be done? And how many p bits, how many private bits can be sent reliably? So what will you do? Of course, you can tell these four states cannot be reliably distinguished, but of course, with these four states, some information can be always extracted. I don't want that any information.
At least 1 bit, I think.
Can you tell me the protocol?
So yeah, if Alice wants to send 0, she will send Psi1, Psi2, and
So Alice will decide, no, I will not send information because it will not remain reliable. I mean, it will not remain secret. That's why she will decide that let me generate 1 bit of private information. So what he will do, if it is 0, then he will randomly choose from this set. And if he wants to send 1, he will randomly choose one of these two sets. Now, can you tell me when Alice is Alice has decided to send 0, then what is the state of if it is half? But I am taking for Alice. Walk. But Alice is sending. And walk can discriminate among them because they are completely orthogonal subspace. But what about if? Huh? Same state. Same state. Because for Eve it will be equal mixture of, for 0 it will be equal mixture of psi 1, psi 2, and for 1 it will be equal mixture of psi 3, psi 4. So it is very interesting that if state is in and same whether Alice sends 0 or 1. This is privacy. So what did you sacrifice here? One. How did you sacrifice? You were able to send 2 bits of information to Bob, but you sacrifice 1 bit to make this thing simple. So you will not be surprised if let some
Sir, in principle, this cannot happen, right? Because you are assuming perfect state is going to Bob, but some information is created.
that's why I told you artificial to understand.
Okay.
But here there is a lesson to learn that if Px rho x is equal to rho, it does not discard the possibility that if you take a subset from this, even you can get this. Because here you see it is equal to rho. No? But if you take a subset, then also it is rho. Because equal mixture of psi 1, psi 2 is 0, equal mixture of psi 3, psi 4 is also. So if you take a mixture of states and if it is rho, then it does not discard the possibility that if you take a subset from this thing, that can also make it to be equal to rho. This is actually the idea of privacy. So I will make if so that each state is always there. So this is the basic idea. It may happen that what now I am going to discuss, it may be immediately clear to you, but the basic physics is here. Sometimes artificial things should be discussed to make their picture clear. Now let me recapitulate.
Why are you saying this is artificial?
As we have studied that we are sending orthogonal states.
Orthogonal state Alice is sending. Some footprint is going to.
It will be like something realistic.
Cloning kind of thing.
No, because they are orthogonal state. What is the cloning? No violation of cloning. You
No,
want to achieve.
of course, no violation of cloning. But I am telling, can you imagine a channel?
No, that's why I'm saying cloning is not restricting. If you are cloning
Yeah.
in mind, that is not the case.
Yeah, so in principle,
Otherwise,
it can happen.
in principle, this can happen. Very peculiar kind of channel. But cloning is not restricted.
Yeah. So let me recapitulate. So Shannon information means from some source X is coming with probability Px. Then we will get a sequence of xi, pxi. Then you collect these bits from the source and make a big n number of n length sequence, n bit sequence. Then How many possible sequences are there? If I take n number, no. What is the total number? If it is bits, then it will be 2 to the power n. So, but we have already seen that we will not take all of them because they will not occur with equal probability. Or not only that, if I take atypical sequence, then the probability of occurrence of atypical sequence is almost zero with the that. So from now on, as I have told you, I will always work with. So number of them will be in H. And if from a source with probability pi rho I comes, then what is the state? What is the state? A state you can think of where rho is equal to pi rho I. Now, if I consider the sequence, how many sequences will be there? Typical sequence. Typical sequence. To the power n s. Now, here there is a problem which was not there. Here it is a very important question that you have got 2 to the power n into s rho number of sequences. Oh, sorry. Number of sequences is number of sequences if you write it as rho 1, rho 2, rho 2, rho 1, rho 3 in this way. How many sequences will be there again? 2 to the power n hx or hi, whatever. But if you consider the subspace on which actually the state will reside, that will be ns rho. 2 to the power ns rho. Now, I was discussing with you that, so if you consider, so this is the subspace size, and here the points will come. Here points means large number of sequence of these rho 1, rho 2, rho 3, all these sequence. Now, if you consider, if I ask you the question, because earlier I asked the question plus minus 0, 1. How many you can distinguish? You told it is 2 dimensional, so only 2 or 2 another state can be distinguished. Now, in this subspace, how many states can be distinguished in principle? Yeah. 2 to the power n. But if you consider this particular string, and these are typical string, so how many rho 1 will be there?
In times sorry. It's n times p1. In times p.
So how many rho 1 will be there in a large sequence?
In times p.
N into
p1.
P1. Similarly, so I for R. Sometimes I'm using this way. Can you tell me, if I consider a sequence like this, is it one dimensional like 0, 1, plus and minus? What is the dimension of each member? In my earlier example, I took 0, 1, plus and minus. What is the dimension of each? Here, can you tell me what is that? If we consider a large sequence, what is the dimension of that sequence of states? 1. Be very careful. Because here it is rho. It need not be closed.
If all are the loops,
So these states is nothing but What is the subspace of this? NP1 number of row, NPI number of row I.
In times rank of.
It is a similar way you tell me, they are like this. 2 to the power n s of row. So NP1. But this is not all. You only consider ith one. So I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4. So what will be the total thing? It will be 2 into NP1 s of row 1 into 2 to NP2 s of row 2. What is the total number? 2 to the power n summation over pi s of. So this is the actually subspace of each sequence. If you consider each sequence, it will have this amount of subspace on which it will be shuffled. Now, if you consider all possible string, even equally likely string, it will cover this whole inverse space so many times. Now, there is two things I will call covering theorem, stacking theorem and covering theorem. So, if you consider a sequence, then it will take some amount of subspace in this. To consider another sequence, if you consider another sequence, they have all these properties, this NPI number of row I, but only this row 1 will come here, that row 2 will come there, so that this subspace will remain same. So for another, it may be this, 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 for another, it may be, for another, it may be this. It will be like this. But again, remember that when we consider 0, 1, plus and minus to send information reliably, how many we choose? 2. Yeah, how many I will choose? And so that they remain almost orthogonal. That means if I don't use the state orthogonal, at least they remain distinguished. That proof of distinguishability is rather typical proof, mathematical proof that you can see from some standard books. But question is, how many sequences I can take so that their subspace will remain almost orthogonal and they will pack this actually effective inverse space. And there is a proof that if from the sequence you randomly choose this number, randomly choose, then they actually and they will remain distinguishable. Because you are not taking the all possible sequences. You are taking a subset of them. And this subset can be taken in so many ways. I mean, randomly you take this subset, you keep it here, then again from the rest, again you choose randomly, it will be again distinguishable, again choose, it will be distinguishable. It is like that. So every randomly chosen, this number of sequences will be distinguishable. So if I want to send some classical information perfectly, then what will I do? I will not take all possible sequences. Only randomly chosen or cunningly chosen this number of sequences and encode classical information, and Bob will be able to distinguish among them. This is the theorem of Schumacher, Volevo Schumacher. Sometimes it is called HSW code. But there is another interesting theorem, very powerful theorem, which actually long back I didn't know. I could have not understood. It is the theorem is telling it is called packing theorem, a covering theorem. This one is packing. That if you choose randomly this mass number, they can be distinguished. And covering theorem is telling
Sir,
yes.
when you are saying this randomly chosen set, then accordingly your measurement has to
Yeah. Question is in physical whether measurement can be possible. They calculated a peculiar. They took some POV and then they saw and calculate the average error. And they saw that it becomes large, this average error equal to 0. So they tell that.
That thing is there in classical theory. So that when you randomly choose that information will also pop. It's random.
Of course, which set is being taken, that will come. That we understand that. That's why, first case, Alice has to inform whether I am sending 0 1 set or plus minus set. That information has to give us. Now I am telling an interesting thing that instead of distinguish among them, let us take all these sequences. All these sequences will give some name. Row. I am writing this whole book one.
In
If you calculate the math, is very interesting. Yes. Now what you are doing, you have taken the sequence which can be optimally distinguished. You are taking equal mixture of them. And it has to be proved, which is a fake ensemble, but it gives you or do not proved. Not this is mixed. You take equal mixture of them, it gives you the original state. Yes, I was trying to tell that if you take mixture of a state and finally it is row, then it does not discard the possibility that if you take subset of them, then also it can be used. So actually you are taking n copies, so actual state is row n. And if you take from this all these possible distinguishable set or some more amount of them, then if you add them with equal weights, you get the row n. Now you are getting an idea.
Is there a force?
Oh, Joanna.
Sir, what is the probability you have written before?
Yes,
That's before summation over that thing.
I took the numbers.
So
I
this
took
should
the
be the
numbers.
cardinality of the HSW.
Yeah.
Oh,
in a microphone.
So there is also a source to try to if this quantity is less, but then there is just a second. Now we do. So this is in the literature they take that there is some fake ensemble.
So that means you are saying there are lots of HSW code items.
Yeah.
Randomly. Any of the HSW code has this one. Because HSW code choosing is random.
Yeah.
So whatever randomly I choose, that has this particular code.
Now you see that if thing if this quantity is less than 4, then I can actually get rid of. This is the physics. So this is sometimes called fake ensemble, and they actually prove in some so so they actually prove that something like this. They are almost equivalent. This is called fake ensemble. This is actual, this is fake ensemble. So with some fake ensembles, actually you can mimic the actual state. Now let me what come to what here. Now I consider a state rho AB with this property that S of B, rho B is marginal of B with respect to rho AB. This will have value. Now we can consider purification of, because I am allowed, if I take a state between this and Bob, to for security or entanglement distribution, what I have to do? I have to give a full chance or highest chance of being correlated with the original state. So in quantum mechanics, there is simple purification is the best. So I consider psi AB. Now key distillation or entanglement distillation from this state have many types. They have many types of process. But we there start with the standard process. We will see how. I will take speed decomposition across this curve. So it will be Px Pxi xi. I can do I can have state decomposition between Alice versus Bob. Now I will what because I have to be little bit fast and if you measure because this xi is the orthogonal set.
So rho AB from my can be rho AB form can be right from the
Yeah, of course.
px this.
Yeah. Because if you trace out x part, but I have to be because main idea I have told I have to be little fast. So if I perform measurement in this basis, then it will be pxi xi tensor
Psi x.
xi b, where rho b is equal to you have to take trace of chi xi b, and trace over which part? Each part. Similarly, you can write xi b, you have to trace over b. So how to calculate overall Bob's density matrix? Bob's density matrix will be rho b will be dxi rho b xi, and what about rho e? Dxi rho b. And rho a, of course, is very simple. Now, if you consider Alice, this means this source that xi is coming with probability p xi. It is like classical. Because they are orthogonal. These states are also orthogonal according to state decomposition. But I am not working the whole state of B. I am working with B and E separately. That's why they become density. But Alice's part will remain pure. So Alice's this thing is nothing but the classical. What about Bob's thing? For Bob, as if with probability pxi, rho bxi is coming. You can picture it. And for Eve, this is for Alice, this is for Bob, this is for Charlie. See, but again with same probability. So you can think of, so if you take large number of these states,
That rho is pxi rho xi like what
yes,
second line
yeah,
should be rho
Oh.
xi.
thank you. You can think of like this. Now, let me calculate another quantity, Volvo quantity with AB. Yeah. So As if you calculate it is called quantum mutual information. If you calculate this quantity, then actually this is after some step, because this is a S of rho A, no? S of A plus S of B minus S of AB. If you calculate this quantity, this will come as finally S of rho B minus Px S of rho Bx. Actually, whole one. Similarly, you could calculate I and you will get again S of rho E minus Px on this. Now, this warrant information can be defined as, so you give it a name, I, X, P. And this is IXD, which I did not write. You could write. This is IA is nothing but this hollow quantity, S rho AB, S rho E minus PX, S of rho X E. Now, warrant information is defined in this way. It has to give a direction. This is actually difference between this quantity. And if you put this thing, this expression and similarly expression for this thing, it will come to be equal to finally S of rho B minus S of rho E. Finally, it's reduced. So if it is positive, then of course you see S of rho AB, S of rho B is greater than, strictly greater than S of rho E.
What is IXP?
Oh, this quantity. This is actually hollow quantity. I wrote. But for this particular case, it can be written as quantum mutual. But we could write it as hollow quantity.
What is the
No, I'm giving, I am just defining. Hollow quantities interpretation, we have seen that hollow 2 to the power n into hollow quantity, that much sequence can be distinguished. That is the interpretation. That I am writing it. Of course, it has a meaning for single step case that classical information about the state that can be achieved is given by this.
So here X is the hollow quantity, that phi.
Yeah, I is that. But here X I am writing X is variable. Sometimes I am using X, sometimes I am writing X. That there may be some confusion. I could write it as XI.
That X is the random variable.
Yeah. So sometimes I am writing X, sometimes I am writing XI. So if I write XI, you know I is equal to 1, 2, 3, 4. When I writing X, you imagine that it is also X1, X2, X3.
It's like that I of XB is same as I of EB.
Yeah.
So X is
So
nothing but
quantum
A.
mutual information, if you calculate, reduces to this.
So, all the calculations you are doing for these steps.
Yeah, but remember these things. If you take many copies of this thing, then to Alice actually it will be sequence of XIs. To Bob it will be sequence of these states with different XI. To Eve it will be again sequence of states with different value of. This is the idea. So now I am coming to here. Right? Oh. I'm writing the full thing that they have taken n copies of this state. Now, so now Alice is measuring on this sequence of x's, this forms a basis on that basis. So Alice will collapse on either typical sequence or atypical sequence. So this Alice of E. So Alice is making this X basis and look at this sequence. And if it is atypical, he is making a phone call to Bob that let us avoid because I have collapsed on atypical sequence. Forget about it. But that will happen with probability anything, yes. If that does not happen, then where you will land up? Some points in this thing where Bob will land up. Where Bob will land up. I mean, the subspace in which Bob will land up.
Or an S of rho. S of rho.
Some sequence of states, but I am giving it a point, and that point will lie in this subspace. What about the it will be a subspace 2 to the power n S of rho. Now, so how many number I can choose from them so that they can be distinguished by what? What is the number that I can choose from these sets? Of course, randomly, but they have to choose from here randomly, but I am keeping them in a box. So what is the size of this thing?
Over
Already we saw
over n S of
2 to the power n
S of S.
S of rho by n is possible. So how many such box I can draw? So you have to divide this thing by this thing, and that I am writing as so. How many are there in this way? How many such boxes are there? So now these points come. In that case, Alice has to tell 0, 1, plus, minus. For this case, which basis he is using to keep that information. Here also, so that Bob can distinguish the sequence, which Alice has to tell whether he is L is equal to 1, to get the name. L is equal to 1, L is equal to 2, L is equal to 3, L is equal to 4, L is equal to 5. In this way, finally L is equal to how many are there? This number. This number I can do the same one. Then I'm again writing this thing. Symbol.
It is that only, 2 power n h of x given b. That many books L equal to that. That is the last number.
Yeah, this is the last.
This L equal to this is the last.
This is the last. So final thing will be 2. So how many bits will be required to give this information where actually Alice has collapsed? How much information will you give?
It's given me. N 60.
Now, this is the picture of Alice. What about the picture of this here? If you take L is equal to 1, then how we have constructed this set that from here it will cover, it will actually pack. Once from here it will just pack Bob's total universe. Similarly, if you take, so this can pack, 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 this can also. So only if Alice is, Bob is given the information, value of L, then Bob will know the L is this, so sequence are this. So, and so the state can be distinguished, so he can extract the information about the classical information that Alice has encoded in those sequence of states. Now, I have taken, now if you come to If's picture, now if you forget about Bob, can you tell me if I consider Alice and Eve, whether this type, Eve can also have this kind of picture or disjoint set, disjoint subsets, whether this side will go up or down. Because Bob is worse. Bob is the row of SD is worse. That's why the size of thing, this thing, even for a smaller size, if this thing will be packed. Now I am making a big picture. Inside, I am taking, because already you told that for him it will be less, it will be of less size. I am taking that to be m. So inside between it will be m is equal to 1. Actually, this is this m means here if you take a smaller set, then it will actually pack if silver space. Now, so I am putting the size of this thing in such a way that it can pack if that. But if you take equal mixture of them, then what happens? It will be equal to box. No, this covering theorem. So for every L, there again for this set also there will be some, again m is equal to 1, m is equal to 2, m is equal to 3. Now there is happiness. Actually, every points from this L1 Bob can distinguish. But now Bob instead of distinguishing, the whole points, if you can distinguish among the whole points, then if you group them, this group also can be distinguished. What is the size of M? I am here writing the size of all these people. So size of these names are, now if you take product of them, what will you get finally? You'll get the whole thing. Huh? Yeah, NHS, yeah. The whole thing you are getting. Now the protocol is something like this. Then I'll do it little bit mathematically, but first let me tell you the protocol. So Alice will make the measurement. If it is atypical, Alice will make a phone call that I have to work on the wrong thing. So let us have a phone call, start again. If it is in a typical sequence, then Alice know this typical sequence will somewhere, yeah, it has a L number. Again, it will have a N number, and also it has a S number. Got all things Alice. Now, if Alice sends information about L, then Bob can distinguish which. Bob can learn which sequence of states Alice have collapsed, or what is the Alice's classical message. And when if can know, if is tell which M is L as well as M, M is publicly announced, but M is not publicly announced. But if M is announced, then Eve also can. Eve also, because it can point within this thing, it can distinguish. Here is the clever thing that Alice will only announce and Bob will extract them because she can distinguish and will not tell anything to. So Alice, as Alice has collapsed, Alice will know L, M, L, M, S, all the information. But he will only inform it. And Bob will decode it. And Alice knows also M. That M is the private key. And each thing will be because if we will have not, if does not information about M, so all M are equal to him. From measurement on his system, he cannot get any idea about it. Clear?
Each M covers each space.
Huh?
Each M
M covers, so that's why it is called privacy amplification set. This is HS port. L is HS port, where Bob can distinguish every points. M is privacy amplification things, which actually if diverse if to get any idea about the information. But actually, Alice could send, if there is no question of is, Alice could send how much information? This much information. But because they want secret key, they have to sacrifice. How much sacrifice? This here, this minus this about gives what? That has to be sum. So they have to sacrifice. So one thing they have to communicate, Alice has to communicate, and second thing they have to sacrifice. And After sacrificing, the rate is actually coincides with this ball in this formation. But actual result is much more powerful. Now let me give you a little bit mathematical. It says among the two. Which every sequence will have a number L, M, and S. Of course, I am assuming that Alice has constant. That's if I write this thing, actually, you consider it to be a density. If I write the ket, then it is. Otherwise, take this is nothing but projector on this. Oh, sorry. Now, so this can be written as because the LMS is nothing but 2 to the power NHX. Now, Alice has announced already L. So, why there will be summation of this? So, it will go to 1 by MS. This L has been fixed, sub L is equal to L0. So, I am not writing.
Because that is public info.
Yeah. I am also not writing it. Now, I am swapping this thing. I am swapping this thing to two states, but two registers because I am writing this thing as
This is new.
again. Remember that all these things are density matrix, but I am for simplicity not putting a K so that we consider it to be a density matrix. So I can swap this thing. Yeah, I can swap this thing because there are n into s number of this thing. So I can swap this thing in two registers. Both are with Alice. Now, Alice ignores this thing. Alice does not care about this thing. So where it will go? Oh, again I am making confusion. If I write in this form, I should write.
Yeah.
Now Alice is not interested in the value of S. I can do it as S comes here. But it is in MS set. So Alice can recover. Actually, Alice can recover AMS both, but S does not recover. So we will take a register and find the value of M. So finally, we get this for A. So Alice will extract the value of M and put it in a register. And Bob's thing, if you trace out B, Bob's thing will be 1 by S, sum over S, rho MS for Bob. Rho S for Bob. Because M is for now for each M. For each M, if you come for each M, it is a privacy amplification set. So finally, this thing you can write as. So this is sum over privacy amplification set. So if is totally, they are sharing secret bits, and if system is totally uncorrelated, because for each M,
Let me see.
So what are you doing to the index L?
L has been announced. That's why I could put everywhere. I could put L is equal to some L1.
But this is for some L that has been.
Yeah, that's why I forget about it. And M has not been conveyed by Alice. Then M has been extracted by Bob. And he could learn the sequence if he's given the information of M. But Alice, when Bob is extracting this thing, he will not tell this thing. So for him, everything is there. But M is not what Alice could, Bob could recover less than that. Not what Bob could discriminate, but much less than that. Because it will be 2 to the power n by xb minus ix.
So in the first example, the 0, 1, plus minus. So L is just announced the basis.
Yeah.
So that is the like announcing the head. The outcome she doesn't have. Outcome is the privacy.
That Bob will recover and he will pay.
Because in both cases it is
Density matrix is. That's why this covering theorem is very powerful. Now, just আমি ইন্টারনেট ডিস্ট্রিবিউশন বলবো এটা শেষ হয়ে যাবে নেক্সট এটাই বলবো একটু কোহারেন্টলি বলবো এবার কি করবো what I will do I will not make this measurement I will make a measurement typical versus atypical. If it is atypical, they will avoid the problem. If it is typical, still coherence will remain. Then they will proceed. Because if you measurement in the basis, then entanglement will be lost. But again, you will see this amount of I mean per copy, this amount of entanglement can be.
One question. So the first example that you gave, the 4 states A0, A1, A2, A3, and the reduced state of E was same. So there, one bit of information you are sending to Bob, right?
Secret.
Yeah, and
Because
no,
for
that
E-
information is not going to E.
Yeah.
Right. Now here, how is the information going? That is not clear to me because where the state will collapse, that is not in Alice's hand.
Yeah, but that does not. So, but he knows whether the number is it, somewhere it will collapse.
Yes. So
Say,
here,
let it has collapsed on LK. Somewhere it has to collapse.
exactly, that is now publicly announced.
Publicly announced.
Now even the M and S is now collapsed somewhere.
Yeah. That. So Alice know N, M, S, all things. Because every typical sequence has a number N, M, S.
Right.
Alice will only announce L.
Right.
Bob will, because of this Hollywood theorem, Bob can extract after knowing L, Bob can get the value of M by performing some measurement.
Right. But
And as he has no information about M, all things are equal.
yeah, but now here the task is to establish some private uh, bit between both of them. So this M is the private
M is
thing
the
between them. But this is not like they are sending some information.
No.
Here
That is
is the
due to
task.
correlation they are creating.
Yeah, means here the task is only
Yeah.
to establish some private bit,
Yeah,
not
yeah,
to
by
send
using a
information.
triangle district.
Because means this will you will use as a key for
Yeah.
for
But here you are distilling key by using physics.
Hmm.
The other day, we assume that this mutual information is greater than this mutual information. Then, of course, if it is guaranteed, then you can distill. But here, physics is telling that this can be made. You have a state, so and this is possible.
Let us go for a tea break. Now it is 10 to 10, 12:10. We'll exactly meet at 12:30. 20 minutes. Right?
Yes, bro.
So who are in online, we will just exactly meet at 12:30. Now 12, at 12:30 we'll meet.
Because these are the states with this state billion.
প্রেমদা আবার নেক্সট প্রোগ্রাম কখন হয়েছে 12:30 ইধারই পাঠান না লোক হ্যাঁ এখন পর্যন্ত তাহলে চলো বেশি বেশি হ্যাঁ ঠিক আছে ঠিক আছে সুইচ ওটা লাগানো হলো 12:30 থেকে ম্যাডাম না তোমার
I will erase this picture, but you keep in your mind this picture. Extend means all possible, but there is typical as well as magic. Extend by extend I means sequence with n. So this is n copies of this same state that we use. Whose density matrix for AB is rho AB in this property. The quantity information will be positive. Now, Alice makes a measurement in this versus subspace on the right. I mean subspace with this dimension versus space. If he collapses on rest, if he collapses on rest, then about the protocol. But if he collapses on this subspace, which contains all these typical states, then he will continue. Sometimes I get she and calculate that is for this I should tell you. So after this measurement, sorry. After this measurement, it will come to here there is 1 by 2 to the power x. But after this measurement, it will be because this is the size of this typical. No, here actually it is not.
It is about n.
Now it is this. Then actually I can swap it to in 3 register I swap. And L that is from L is equal to 1 to up to that, M is equal to 1 to up to that, and S is equal to 1 to up to. Now Alice measures after this thing. Alice measures in the L basis. And publicly announced. So what will be the state after that? The L has been fixed. Now I can write it as MS. I should write L is equal to some L0 or something. But now he is ignoring that register also. So I erase it because L has been fixed. No, it's a pure state.
That is just
So it will be M is Q is A start sign because L has been fixed. I am erasing. Now already you know. Now actually there actually Alice was not using his whole power because if he can get L, he can get the value of MS itself. No, but because we are not interested in the whole MS, because S will, then S will also get, E will also get some information. That's why Alice was not, Bob was not distinguished through the whole points. But actually he can distinguish whatever points is there in a particular L. And now in a particular L, how many points are there? M into S. So he can make a measurement like this. He would be then star x then ms, sorry, and put another register in B1 so that this becomes ms, because he is not coherently, he is coherently getting the information of ms. And this is B1. I'm writing B1 first. So this state becomes I can put this as also M and this, because I can swap this thing to M.
Sir, that unitary is on B1 system, right?
Yeah.
First.
Yeah. This is my state. It looks like as if Harris and Bob is sharing a maximally entangled state. It is not true. Because if you trace out the
Yes. That part has,
That has some information.
yeah. And also, no, but I'm telling that you cannot write it as this thing tensor this thing. Because MS, you have taken sum over MS is there. But what you can do now,
But like, at least, can we say this, like, Alice and Bob has at least that log m amount of angle.
that you have to extract. So you have to actually separate it out.
Yeah.
And you know, actually you get n bits of entanglement.
So that,
Now it is still MS, is large.
yeah.
So you have to get rid of S register. So that the sum over will come there. This is the challenge. Now, Alice can make a measurement in the basis T, which is, I mean, Fourier transform basis. This is, so S is the basis. From S you can construct Fourier transform. And Alice is making a measurement from this Fourier transform basis on his system S register. So he will collapse on say P is equal to P0. Then Alice will throw out this A3. Then what will remain? After collapse, it will collapse on say some T is equal to P0. It will collapse a particular value of T, single T, because he is measuring in this basis, and then forget about A3. Then what will be the state? E to the power 2 pi I S T K, say K thing in scholars. Now, Alice has to get rid of this thing because still that's why my thing is still. So he has to get rid of this thing. So what he can do, he can do some controlled operation, controlled phase shift based on this. Control phase shift is so Bob apply phase shift, which is
There is some capital S missing.
right,
Should be divided by capital S.
so he is applying this phase shift. On S resistor. So he will get rid of this. Maybe it is only minus. No? So we'll get rid of S. Bob will apply this phase shift operator on this thing, and he will already there were this phase, so this phase will cancel out. So finally, what they get? Demo. I believe I think same.
But Bob has to know TK, right?
Yeah, TK has been announced.
No. The outcome is
Oh, that I forgot to say. TK has been announced. After this collapse, TK has been. Now I define the state. Oh, but Bob's thing is still there. This thing is there. Now I define. I define this. Now, this has state has a nice property that if you trace out most part then what will have? What will be for B? Place out box. Come to privacy amplification set.
EV is always fixed.
Place of B of this thing, okay, if you take density matrix form,
I
because there will be sum of only S and there is one by S. Now, so this is true for all for M. For every M you can write whatever M you take, if you trace out this part will be, so this is for all M. Imagine this M set, you know, is those points. If you take equal mixture of them, this gives you originally its originals. This privacy amplification of what we call cover. Then can you tell me that what will be phi M1 connection between phi M, say phi one with phi M? Can you tell me one? So this is true. This is true for M is equal to 1, M is equal to 2, M is equal to 3 for all of them. Now can you tell me what will be the connection between phi 1 and phi M? So both of their E parts same. So what is the freedom? So I write in the reverse way so that it will be complete. So I can connect every M to M is equal to 1 by this digitize. So after this thing, this state will be now you can get, of course, but instead of that, we can write B, B1,
That V would be V. Technically, V would be V.
Yeah. That's right.
yeah,
V.
alright, it's of B. B. Because B1 will remain like this. If you want. Phi 1. No? Now this has been a fixed state. E. This has been a fixed state. But we have to still we have this, oh no. What upon S that?
No, that is
Oh, M has
considered
been
in
captured by
5M.
So Now what you have to do? You it's from one, two. Now you apply this control. Bob applies this controlled unitary operation. After this controlled unitary operation, this will be and don't forget about this delays. This is the Maximilian time state. So here where we use the privacy amplification, privacy we use that this for all m this is the schematics of EV cell. That's why you can use Union's theorem as you told that they can every m is connected by unitary operator. You put the unitary operator, then control by controlling on m, we take a control unitary operation so that we get rid of this unitary operator, and finally we get is a state between Alice and Bob. Insert some part of B into it, but which is the fixed. Now you could ask me that if this amount of maximally entangled state can be distinct, then this much amount of key is automatically distinct. So why did I separately treat key distillation and entanglement distillation? Only to prepare our mind. But if you do key distillation, you get a clear picture. Only thing here you want difference between these two. In that case, from initial stage, Alice collapsed. But here you have to maintain the coherence so that in the m variable you get the maximum assignment.
Earlier case, the information of S is not used in the whole of the product.
Yeah.
But now, to keep the preserve the coherence, we have to typically Alice has to use this S information.
Yeah. Because now Alice, in that case, actually Alice could in regeneration case, Alice could extract M and S, but he is interested in M because S he will not do because he wants privacy. But he knew S. Here he is extracting both the information. That's why you get MS versus MS. We started with MS versus MS and the rest. Then you have to get rid of S. This is the so how to get rid of S? First, measure in Fourier transform basis by Alice, then get rid of the phase coming from the Fourier basis, then use Ullmann's theorem,
And then
control unitary operation, and you will see that if system and part of Bob system will be totally uncorrelated because the then variable does not appear here.
Actually, communicating information about T doesn't communicate anything about S.
Yeah.
That is the
Yeah. That's why you mixing all of them equally.
Yeah.
Is the tricks. I'll go to little bit. So maybe some parts may not be clear, but basic physics idea of physics is coming from the starting itself. I told that. Remember that 0 plus minus physics. You can remember this physics. This is just mathematically non-trivial. It looks mathematically non-trivial, then it is not mathematically non-trivial. If you forget about the proof of this thing, or about the environment of this thing, the proof may be more complicated, but otherwise, if you remember these things, then it is not that complicated, and the physics is very simple. But still, this privacy in 1990, Schumacher and Westphal wrote a paper where they told that at least we can have privacy which is greater than equal to warranty information. But it was not proved that that much amount of entanglement also can be distinct. This was not proved, but this was conjectured by some people who were very mechanics. They used to think, but for Bell mixture, they could prove that this amount can be distinct. But I cannot, I have not been, there is a two protocol, hashing protocol and bidding protocol. Bidding protocol, I understand, the hashing protocol, I didn't understand. I can manage subject this hashing protocol. But for general state, no one could prove for a long time. And actually, it depends on, they could not prove, I think, because this covering theorem, packing theorem was known, because it is HSW theorem. But this covering theorem, but to take equal mixture of the region to original state, this theorem maybe it was not there. That's why they did not. It was proved in 2004, was by Deveta himself, or latter paper written by Deveta. ERL paper there is a proceeding of. Now I'll come to quantum error practically. So how much time money I can take? Or I can stop here, no?
Or you can take some time, no problem, if you are energetic.
Yeah. Now you are sending a qubit, or a qubit is there. What is the problem? Problem is that it may correlate with the environment. And on the environment, you have no control. That's why, in general, you will not be able to recover your original quantum state. This is the problem. Now, what is the most general operation? So, you to consider a qubit, so 0 in equals to some 0 0 0 0 plus 1 and in this way you can write. I'm not normalizing the state. You can write in normalized way. But this is the most general thing, which can happen to a qubit. Now, question is, if these are only the two states of qubit, then they are orthogonal. But this is not quantum information. Quantum information means any state in a two-dimensional subset. So now you do some mathematics, or you can look at this thing. It can be written as A0 plus B1 picture of, not picture, superposition of this thing plus not exactly this thing. It is now E00 minus E1. Similarly, this will be E01 plus E1. and 0, 1 minus 0. You do this calculation also. But now there is a nice thing. What I can write this thing? This is my psi. What is this? This is psi. This is sigma. So Z psi. Z instead of sigma I write Z psi. This is X psi. This is XZ psi. So finally what you see that psi after this correction, the qubit state is going to some psi plus with some environment E1 plus X psi with some environment E2 plus Z psi some E3 plus XZ psi. Oh, where E1, E2, E3, E4, maybe if these are orthogonal and if these are not orthogonal. Does it make any sense for you? Or recover the state? If they are orthogonal, still what you can. It is not in your hand. If environment is in your hand and they are orthogonal, of course you can make a design and know that which corruption has occurred. And so that's why people used to think, as the environment is not in my hand, there is no way you can recover it. Because this is a continuous transformation. I have not written the coefficient. There may be infinite possibility of coefficients. So people used to think that quantum computer may be a theoretical thing, but it can never be implemented because quantum interaction is not possible. But so environment is not in your hand. But fortunately, if you make a measurement and corruption on of them, then you know the error and correct it. You collapse on psi first term, then you know there is no corruption. If you collapse on X psi, then you know that X corruption has occurred, you correct it. Similarly for second, similarly for third. But question is, are they orthogonal? For a single qubit, they are not orthogonal. So what is the challenge? So if you have to encode your quantum information in more than one qubit in such a way that at least if one qubit error occurs, you can get rid of. This is the science of error correction. I give you one example. Historically, so this has been one point nice. So there is maybe continuous set of error, but you can discretize. Now I am writing. I am taking my state. This is my qubit state. Huh? But I am encoding it in where this is encoding. Where this 0L is equal to 9 qubits. I am taking 9 qubits. I could write, and there will be 2. First, now when you will be able to correct the error, if after the error it goes to a orthogonal state, which you can discrete. Now, first forget about 1L or take 0L. If there is an error in the first qubit, say X error, then will it be orthogonal with the original state? First qubit has suffered X error. then what will be the state after this error? It will be 1 0 0 plus 0 1 1. This for the first 3 qubit, and other 2 will remain same. Plus, I am writing plus means this is plus 2. So this is orthogonal to this. Huh? Now you can arbitrarily tell me any correction, maybe 1 qubit correction. I will show them you that is state will be orthogonal. You arbitrarily tell me any correction.
Any arbitrary unitary or
Any arbitrary unity I need not consider because they are linear combination of them. Then I will have some one of them. Jet correction on which qubit? Third qubit. So this will be this is orthogonal to this. So for each 0 whatever correction around qubit happen, it will be orthogonal to the whole. And not only that, for different corruption, they will be also orthogonal. No, I'm wrong. For different corruption, if they are orthogonal, that is good, but it is we are using huge number of qubits. That's why if jet corruption occurs on first, jet corruption occurs on second, they are set. And jet corruption on third again set. But it's just different set. So this is equally what for 1L. So if this works for 0L and 1L equally, then it will equally work for. Now I am giving you a set of unitary operators. Next is identity. This is I3, I4, I5, I6, I7, I8, I9. Z1 on. So I am just defining operators. Then rest are identity. Then Z4, Z5, rest are identity. Then Z5, Z6, rest are identity. How many operators are there?
Z3, Z4 also.
Z4, Z5, this. Then Z, then Z8, rest are identity. And Z8, Z9, rest are identity. Then X1, X2, X3, X4, X5, X6, rest are identity. And X4, X5, X6, X7, X8, X9. So how many operators are there?
4 is them.
8, I think it is 8. 8. You name it. M1, M2, 2. You can check that they are all common. So they can have
So there one is remaining.
M8. If it is not M8, then at least 2-dimensional substrate they cannot protect them.
Like some symmetry. X1, X2, X3, identity, X. That is not there.
By action of this last two, you can get that. This applies.
No, now I am telling you. You can check that 0 and then 1, there both are eigenstate of all the operators. I mean, all are eigenvectors of all MIs, and MI is commute because MI is commute, and with eigenvalue class 1. And now I am telling, if you take any single error, that will anti-commute at least with one of them. And another thing, that all these operators can be measured simultaneously. So if you measure them simultaneously, at least. So if you take the state is this, then if I measure all these 9 operators simultaneously, what will be the all these 8 operators? What will be the result? All are plus. Now, if some whatever error you consider on 1 qubit, you will see if you measure all 8 of them, at least somewhere it will be different. Somewhere maybe 1 minus 1 will come, sometimes 2 minus 1 will come. But still, you see how many dimensions are there for these 9 qubits? 9. And so on 9 qubits, 3 or each qubit there are how many possible errors? 3. 3 into 9, and I want to protect 2 dimension. So how much it is? 56. But actual dimension is much higher. So there are much scope to use the rest of the thing, but it is degenerate. Because you see that first qubit, second qubit, third qubit, Z error is giving you the same state. That's why it is not covering the whole thing. So for n qubit, one means I am taking that there is no corruption. That is also a possibility. Plus n number of qubit, 3 possible correction is there. I want to protect a 2 dimension. It should be less than 2 to the power n. Otherwise, error will 1. So can you tell me what is the optimal number of n that it can satisfy? 2 qubits error correcting code is possible.
Is n equal to
5.
it will not. N equal to 5 it will.
That is non-degenerate. Every different before operator will take you orthogonal subsets. And indeed, 5-bit error, 5-qubit error correcting code is there.
So how this relation is coming?
So how many 2 dimensional? How many 2 dimensional you have to get? You have to give them a space. But that's why this is very not efficient. But its form you can remember. But if I take 5 qubits error correcting code, there will be 16 terms of 0, 1, 0. So this is more complicated, but otherwise tight. Non-linear. This is 9 qubits, which is very easy to remember. Not only that, historically it was discovered first by Solomon. So what you can do, you can check that if you consider all these 8 operators, they commute within themselves and they can stabilize a 2-dimensional substance. And that 2 dimension is covered by this, spanned by 0 and 1. Next day, we will discuss 5-bit error correcting code, but more importantly, we is the CSS code with the aim, mm, to have a BB84 protocol, which is unconditionally secure, but from the angle of if they just BB84 protocol and say you are doing BB84. So you send many copies, compare those results, compare the bases, in which case the basis is not match, you throw them out. You get those where basis matches, then some parts of them you can take and compare the results. If there is error, if there is it, then what you can do? Generally, you have to throw everything. Or, but this is not a very practical thing. There we will see using CSS code that if error is not much, if error is my capacity of quantum error correcting code, then actually from the base we can distill it, but we can make the less. The privacy distribution.
Sir, here we are getting 1 plus 3 n times 2.
One is uncorrupted. N qubit, each qubit may be corrupted in 3 ways: X, Z, XZ. So there are n qubits. So totally there are 3n corruption. Like 1 plus 3n, and each uncorrupted or corrupted, each will have dimension 2. So this should not cross to total number of total his persons.
But uncorrupted should be 0.
You have n qubit, you have 2 qubit, 2 qubit information, you encoding n qubit. Now what can happen? None of the qubit is corrupted.
That you have to take it out.
So first qubit is corrupted. Now first qubit can corrupt in how many ways?
3 ways.
Second qubit can corrupt how many ways? So how many possibilities are there? Plus 1. Okay. So for each of them, you have to encode a two-dimensional subspace. You have to secure, means ensure. And what is the number of qubit you have used? In what is the total dimension?
That should not exceed. Correct.
At least that much dimension should be present.
This should not cross. What? So condition is, if it is equal, very good. But already this is much less than this for 90. So this is very non-linear kind of. It cannot use the full. But if you take 5, the mathematics is telling with 5 you should be able to do. But indeed there is 5 in it. But that cannot be simply written in this, because there are 16 terms. How to write that terms, that I will discuss. So this is very powerful discovery, and this is called a stabilizer formula. And you can measure them simultaneously because they are counted.
So can we just take one example? If suppose there is Z error in the first qubit, then what will happen for all of them?
Then I will tell you.
M1 will be 0. M1 will be
Minus 1.
minus.
One of them will be
M1 will be minus, rest all will be
Plus 1. And similarly, like, yeah, I understand. But if there is an error in 2, then M1 and M2 both will be minus. Okay. So looking into which values are plus 1 and which values are
you are
minus
identifying
1,
which qubit has
which
raised,
qubit
is
which
corrupted.
error is happened.
Which qubit and which error has been.
You can make a list table, but it will be so big.
Yeah.
Very difficult. So when thing is, error may commute with some of them, but at least it will anti-commute with at least with one of them, but it may anti-commute with more than one of them.
So by this measuring, we are collapsing on a particular error.
Yeah, particular which you know which qubit has been corrupted and which particular error has occurred. That's why you
Yeah.
can.
Yeah. So by the measurement, we are actually creating the particular error. Like
So main thing is, so after passing through the channel, you perform the measurement of this naive. In which point you are getting different eigenvalues, you know from your list, you will know which particular qubit has been corrupted, which corruption has occurred, you correct. And then, so you are starting with A0B1, then encoding it in A0L plus B1L, then passing through the channel, and somehow guarantees that no more than one qubit has been corrupted. On the other side, what you can do, you can make the measurement of these 8 operators, and if all are plus 1, you are okay. Just the quantum information has come correctly, but if some of them is minus, then you know which particular error has occurred on which qubit, then you can correct it, and finally you get A0L, B1L, and then again you can decode and get the information in your one qubit A0 plus.
Looking at the plus minus value, we can know that which qubit has error.
And which error?
Which error? Suppose Z error. But that Z error can occur from the second qubit as well as first qubit.
Yeah,
Suppose my
that's why you can do your correction on any qubit.
That is specifically which qubit has the error that we don't know. So we just apply that
Yeah.
error in any one of them.
Yeah, for this case, because there is degeneration. Each block, first three, for the second block, first three means for first three, 1, 2, 3, Z error is same. 4, 5, 6, Z error is same. 7, 8, 9, Z error is same. So you can correct any one.
But we don't know actually which qubit has suffered
Yeah,
the
you need
error.
not.
Because it is same.
1, 2.
Sometimes it can correct it.
Actually, rest of the thing, it will give the space to 2, 3, maybe 8, because so much space is there. So it can, of course, it can be home to some of 2 qubit, 3 qubit error. But it cannot cover the whole 2 qubit error. That's why I cannot tell this 2 qubit error.
If I have some particular knowledge about
So it's maybe some particular 2 qubit, 3 qubit error also. But it will not cover the full
general.
There's so much space is left.
Those things also can be done, like you encode it in even higher dimension so that any 2 qubit error can be that also.
It will be complicated. It will be engineering work,
Yeah.
but in principle.
So, any question? Very quick question if you have.
Yeah, DN Chuang or and do the search to have the quantum electric and something will come. Make it some but I always prefer for this particular thing, basically is also good, but somehow this DN Chuang is the best. Discussion.
Manmin has one book. No?
Yeah, I got a book because I will need.
Okay, let us thanks Guruda for today, and we will meet again day after tomorrow, same time 11. Okay, thank you everyone.
Thank you, sir.